So, let's do one more chance. It's 3 different groups coming.
Does anybody need the mass spec handout or the quiz physical copy? All right, yeah, just keep your hands there.
Just the quiz.
Just the quiz? Okay. You need just the quiz?
the mass spec.
Mass spec?
Is the mass spec the one we got last week?
Yeah, the packet. Yeah,
Good afternoon, everyone. Let's go ahead and get started. I'd like to begin with a prayer, and so I am looking for a volunteer. Please.
Heavenly Father in heaven, we thank you, Father, for a beautiful day that else bless us with. I'm grateful for the opportunity that we have right now to study. We pray, please, that the Spirit will be upon us, that we can focus and we can learn the things that we need to be useful in our lives. And we love you, Father, and say things in our Savior's name, Jesus Christ.
Amen.
Amen.
Thank you. Okay. A comment or two about the quiz and how one can turn it in. There are several options. You can bring it to class on Wednesday. It's due at 5 p.m., so if you need the extra time, obviously, that's not a good option. But if you have it done, you're welcome to bring it then. You can bring it by my office, which is in the Benson building on the 2nd floor, C201, and slide it under the door if I'm not there, but often I am there, so you're welcome to do that. You can leave it in the department offices. So I have a mailbox in the main office of the department, chemistry and biochemistry. You can leave it with the student secretary as you go in the door there. Or there is a drop box for us. Our class has a display case in the Benson building and in the main hallway, east-west hallway. The display case is labeled, and next to the display case there is a wooden cabinet with slots, and we have, I think, 3 slots, 1 for each section. That doesn't really matter, but that's how they've set it up. You can leave it there, or you're welcome to attach your quiz to an email and send the email to me. Please don't use my Learning Suite email. I don't monitor that. I don't look at it. I don't want your quiz to get lost. So send it to my departmental, my BYU email address, which is on Learning Suite, and it's also listed on Learning Suite and also on the syllabus. So any questions about that? All right. We are going to transition to chapter 4, but I wanted to talk for just a couple minutes more about mass spectrometry and to try to make sure that things are understood there. So let's see here. You want to make sure I get to the right place? Is that what you see now? No, okay. Sorry. Okay, we have to. Oh, okay. Okay, so we talked about MALDI mass spec as the way traditionally, historically, the proteins have been identified using the approach of fingerprinting, peptide or protein fingerprinting, where you purify the protein, digest it with trypsin, you measure the masses of the fragments produced, compare them to a database. If you get identical masses or near identical masses experimentally as compared with the database, then you know the protein. So this is not a very good method for quantitation, not for the primary reason that to get the protein in the first place, you have to carry out several purification steps. And the problem with purifications is that you don't recover 100%. You get variable amounts back. Even if you're working with the same protein, the same protocol, you think you're doing it the same way, you can get as much as 50% difference in how much you end up with at the end of that same purification step. And now if you combine 6, 8, 10 purification steps, you'll quickly realize that how much you get at the end may be a poor reflection of how much you had to begin with. Does that make sense? So as a consequence, it's not a very good method for determining how much was there. Now, if you do two-dimensional gel electrophoresis and you become skilled at doing that, the intensity of those dots, if you're doing comparisons between two different tissues or two different states of a tissue, between stimulated cells and unstimulated cells, the intensity of those dots in general is a pretty good reflection of how much was there. Because with 2D gel electrophoresis, all of the purification, or most all of the purification, is happening as part of those two gels, and you're not put in the position of having to recover things. It's just there, and you move it from one gel to the next gel, and you look at the intensity of the spot. So in that sense, it is the 2D gel electrophoresis that is quantitative, but using other purification methods, multiple purification steps, it's hard to know how much you had to begin with. On the other hand, if you use electrospray ionization coupled to a column, and you put on let's say a cell lysate, or you do a homogenate of a tissue, or you use some other biological fluid, in general, you're able to get relative differences between two comparison groups. So again, if I'm looking at cytosol from stimulated cells versus cytosol from unstimulated cells, I run these, I move these directly onto a column, and from the column onto the mass spectrometer, I'm able to get comparisons now of potentially several thousand different molecules for each for the control and for the stimulated cell lysate. So in this way, you can monitor hundreds, thousands, sometimes even tens of thousands of different species using electrospray ionization. Okay, so that's one thing to remember, because you may have to answer questions like this at some other point. Additionally, I have to tell you that different proteins will ionize differently. What does that mean? It means that if you have a primary amine, it accepts a proton and becomes positively charged very easily. Consequently, for something that contains a primary amine, you'll get a very strong signal. On the other hand, if you have something with just a histidine, it doesn't ionize as well. It's not as strong a base. It doesn't accept that proton as readily. Consequently, you may get a weaker signal for histidine than you would for, let's say, a lysine, even though you have the same exact amount of the two. So what that means is that if you're trying to carry out quantitative measurements, actually, true quantitative measurements, exact quantitation using mass spectrometry, you have to have standards. Okay? You might want to remember that. Okay. So if you're trying to do exact mass, you generally produce a molecule that has a heavy isotope present. So you replace a hydrogen with a deuterium, a carbon-12 with a carbon-13, or some combination of these, and they will have the same exact chemical properties. Your standard is then a heavy isotope analog of the compound of interest, and it will behave identically in the mass spectrometer. It will behave identically in the separation step, but in terms of its mass, it will be a defined number of mass units heavier. And so you can keep track of these, and if you have twice as much or twice as big a peak for the standard, and you know that you had 10 picograms there than what was naturally present, then you would know that you have 5 picograms in the actual specimen. So these are ways of carrying out these different steps. So any questions about this? Yes.
I just don't understand why you have to use like a carbon-13 or a deuterium as opposed to like a regular mass atom.
Well, so the answer is if I'm trying to, okay, there are two parts to this. One is I'd like to be able to distinguish what is naturally present from a known amount of standard that I'm adding. If I don't have a heavy isotope analog and I add simply more of the material that I'm trying to measure, let's say norepinephrine, then I don't know if it came from the specimen or if it came from my adding it to it. Okay, so that's the other aspect of this is that it's best to run the specimen with the standard in it. I mean, all the processing, the same mass spec run and so forth, because it turns out that mass spec runs are somewhat variable. And so if you are running things on different days, you get different sized peaks for the same specimen. And so it's best if you can run them as part of a single run so that they both experience the sensitivity of the instrument, any electrical noise in the system, any impurities, you name it. All of those conditions will be identical for both the heavy isotope analog and the native material. So, all right, let's go ahead. Any other questions? Anybody online that's got some? Okay, well, we're going to leave this now, and we are going to start talking about protein structure. And we're going to talk about various levels of protein structure. We'll talk about those in just a minute. We're going to talk about a couple features that are common structural features that are found in many proteins. These are the alpha helix and beta sheet. And we'll talk about a couple structural proteins that have a dominant secondary structure, which ends up being sort of the overall structure for the molecule. Yes?
Well, we got two questions. There's one that said, how do you create standards? And you add standards, you make sure people are running the MS.
Okay, so the question is, how do you create standards? In one sense, these are commercially produced. Okay, so you fill out an order form and you say that you want to replace your alanine with a heavy isotope version, and you want this company to synthesize this protein for you. And so it can be fairly expensive. These isotope analogs can cost you several $1,000s for a milligram of material. But that's really what it takes. So if you're in the business, let's say, of measuring insulin, and you need to have a very exact measurement of that, then it's probably worth the money investing this. Now, poor man's approach to this would be the following. While it's ideal to have them both present at all times, both the standard and what you're looking for in the specimen, another alternative would be to go down to the drugstore, let's say, and buy some norepinephrine and make up a series of standards and then run them one after another on your mass spectrometer and look at the peak height as a function of concentration. So if you do that, then you can get a plot of concentration versus peak height, and then you can run your unknown, your specimen, and see how big the peak is and compare it to this standard plot. Okay, so that's another way of doing it. Okay, I think I answered both of those questions. All right, so the concept is that proteins have one final low energy three-dimensional structure, okay? This is called the protein's conformation. It's called its native state or structure. It is what is biologically active. If you cause the protein to unfold, you lose its function. You lose its activity. So if you're talking about an enzyme, if you heat it up or if you denature it by adding something like an organic solvent like ethanol, or you add acid, a lot of acid, change the pH, it will cause an unfolding of the protein and a loss of its native biologically active structure, and with it you lose function. Okay, so there are sort of 4 levels of structure. We refer to the amino acid sequence as the primary structure. So that's just the convention. It's just a way of describing this initial level of organization. So if you have one amino acid sequence, you will get one structure. But if you alter the amino acid sequence, even slightly in many cases, it leads to a different looking, a different shaped protein that will have either no activity, or it will have reduced activity, or even a different activity. So by changing the amino acid sequence, we change structure and we change function. There are secondary elements. These don't represent the overall protein, but they represent regions within the protein. And these are recognizable structures. We'll talk about 2, the alpha helix, the beta sheet, that are observable. They have certain dimensions, certain properties, a certain look to them, and they can represent either a small or large portion of the total protein. The tertiary structure is the final 3-dimensional structure of a protein. It is the native state of that protein. Quaternary structure refers to complexes, where you have more than one protein joined together in this sort of supramolecular complex. And these also have very defined structures. Okay. I want to talk just a minute now about the peptide bond. So as we're considering how proteins adopt certain shapes, as we consider why certain structural elements occur within proteins, it is useful to understand that the peptide bond is a very rigid planar system. So as shown here, when we describe this, we often look at this as if it were a carbon-nitrogen single bond, but that is inaccurate. What is really the situation is we have delocalization of electron density over the oxygen, carbon, nitrogen system. So we have partial double bond character over these three nuclei. And as a consequence, this bond is rigid. It is like a board. Now we do have other, so that's what this is trying to show here, is that our peptide bond here is planar. We do have these other carbon bonds and nitrogen carbon bonds where there is some rotation possible. So the carbon bond is considered to be so here's the carbon, let me get a different color here. This is, oops. Where is it? Okay, well, this carbon bond here, carbon nitrogen bond, is called the phi angle. This carbon bond is called the psi angle. So the rotations around these are represented by these two Greek letters, phi and psi. The consequence of this is that this polymer of amino acids really is restricted in the conformations, the rotations that it can achieve. So the carbonyl, the peptide bond is entirely planar. It's just flat. These other bonds actually are limited, and they are limited because of the size of the R side groups. The consequence of this is that there are really limited rotations that are observed in nature. Now, this is a very complicated plot. You won't be expected to know this, but I want to point out a couple features of this. This is called a Ramachandran plot. Not something you need to know, but what it does is it looks at actual phi and psi angle combinations in proteins. And the more intensely blue a region is, the more of a particular pair of angles you will see. What you observe is that you don't have many angle pairs. In other words, all of this gray area means that they don't exist, that those angles do not exist in nature. And so there are these two regions so this region up here and this region here represent the vast majority of protein angles that are seen in actual proteins. These are folded, three-dimensional proteins that are studied by X-ray crystallography, and they're able to determine these phi and psi angles. So what does that mean? Well, it means the following, that these angles tend to force the protein or the polypeptide into certain structures. And if you look at the top one, you'll see that we see beta sheeting. And if you look at the lower one, we see down here, we see that this is associated with alpha helical structure. So what is this telling us? Okay, let me move on to, wow, okay, let me get the stuff. Okay. So let me just sort of spell this out. So if we're trying to fit these side groups together, there are ways that are more accommodating. Think of these side groups as frequently quite bulky. And so we need a way of positioning the side groups to minimize steric hindrance or collisions between side groups. So this can happen most easily in two ways. One is to have the side groups oriented 180 degrees away from one another as you go from one amino acid to the next. Does that make sense? Okay, so rather than having them positioned here where they're bumping into one another, if you orient them 180 degrees away from one another, that allows for spacing large bulky side groups in a way that is as forgiving as possible. The other way of doing it is to create this spiral. And you position now the side groups about 120 degrees away from one another. And since you're going in a spiral, you're also taking a step up. So there's distance between, up and down, between two adjoining amino acids. And you're orienting the side groups somewhere between about 100 and 120 degrees away from each other. This is what you have in an alpha helix, this spiral staircase-like structure. So these represent then ways of accommodating actual physically large side groups within proteins. Okay. Questions about this? Just want to, so, okay, already we're limited by the planar nature of the peptide bond. Now we're also imposing the volume of the side groups. And as a consequence, some of the only structures that work are the alpha helix and the beta sheet. So these are not magical structures that, you know, that look beautiful and were introduced for aesthetic reasons. These are practical arrangements of bulky amino acid side groups. Okay, let me try to go back. Let's see, I have to do what now? Hit the share and go back here. Okay, so that's in effect what is being shown in this plot, that most arrangements, most pairing of phi and psi angles are not possible. Okay, all of the gray space means it doesn't exist in nature. And these two regions that are really dominant are beta sheeting and alpha helical structure. So let's talk about the alpha helix. As mentioned, this is a spiral. The amino acid polymer is spiraling. It is turning in a right-handed direction. So remember that. For one turn, one rotation of the polymer around the central axis, you extend the polymer 5.4 angstroms. So rise over run is 5.4 angstroms per turn. That means that for each turn, you have about 3.6 amino acids that are part of the chain, making that one loop around the central axis. Now, there's another benefit to this. It turns out that in doing this, you orient the peptide backbones. Okay, remember these planar systems. you orient them in such a way that you actually get hydrogen bonding between every typically 4 amino acids, but between every 3 and 4 amino acids, typically every 4 amino acids, you have hydrogen bonding between the carbonyl of one peptide bond and the hydrogen that's on the nitrogen of the peptide bond that's 4 amino acids further along. The amount of alpha helical structure varies greatly between one protein and another. In myoglobin, hemoglobin, it represents, you'll find that 75% of all the amino acids are in one alpha helix or another. But in other proteins, there's no alpha helical structure whatsoever. So it depends really on the side groups that we're talking about. Some amino acids are found more frequently in the alpha helical structure than others. This chart is not something you need to memorize, but what it shows here, if you have a high number, it means that this amino acid is very rarely, if ever, seen in alpha helices. So if we look at glycine, right here, you'll know you can see that it has a number of 4.6, so high numbers, less often found. In fact, glycine is almost never found in alpha helical structure. The other one that is not found in alpha helices is proline. These two can be thought of as actually disrupting the alpha helical structure. Proline, I don't know that you recall, but if you look back at the structure of it, it is cyclized. It has this ring structure, and this puts a kink in the peptide chain. Wherever it occurs, it puts this very acute angle in there, preventing or making it impossible for the polymer to adopt alpha helical structure. So both glycine and proline disrupt alpha helical structure. That's a fairly true statement. Okay. This is a concept that's a little bit hard to follow, but the alpha helix, because of the orientation of the peptide bond, so the carbonyl of one and the nitrogen with its hydrogen of another peptide bond, and this hydrogen bonding, there is actually a overall dipole that is created because of the orientation of these groups, one versus the other. Also, you have the free amine at the N terminus, which is going to be positively charged, and you'll have a free carboxylate, a COO minus at the other end. Consequently, because of the peptide bond, hydrogen bonding along the backbone of the alpha helix with the N terminus, C terminus, there is an overall dipole to the alpha helix. Well, what does that mean? It just means that this contributes to the stability of the alpha helix. So if you can organize things so you don't have opposing electromagnetic forces, if you can align them in a certain way, then that stabilizes the overall alpha helix. Okay, so this now shows us the general organization. This ball and stick really doesn't do justice to this, but what you can see here is the hydrogen bonding of the carbonyl of one peptide bond with the nitrogen with the hydrogen on the nitrogen of another peptide bond 4 amino acids away. So you get this interaction between these two, this attraction. And that is true for every carbonyl and every nitrogen proton that's part of the peptide bonds. And this tends to, again, provide stability to the alpha helical structure. The other thing I wanted to mention, and this is shown here on the right, is that this arrangement is very compact. Okay, you'll notice that if you look at the purple, those are the R groups. It doesn't really tell you if they're large or small. It shows up as a single atom in this depiction, which is not true. But if you think of those as being actually sometimes really quite large, something like a tryptophan or a methionine with an extensive hydrocarbon chain sticking out, you'll realize that this is actually pretty good at separating these R groups one from another. So they're both stacked and they're rotated away from one another, allowing for large bulky groups to be positioned in space in such a way as to minimize steric interactions. However, you can't always achieve an alpha helical structure. If you have several bulky side groups right in a row, that will disrupt the alpha helix. You'll need to expand the distance between them. That will disrupt the alpha helical spiral structure. Additionally, if you have a glycine or a proline, that will disrupt the structure. If you have two groups, so if you're talking about side groups that are 4 amino acids away, they're somewhat placed on top of one another. If those both have, let's say, a negative charge, so you have 2 lysines 4 amino acids apart, again, you have electrostatic repulsion that will disrupt the alpha helix. On the other hand, if you have a negatively charged carboxylate, an aspartate, and a positively charged lysine, 4 amino acids apart, that tends to stabilize alpha helical structure. If you have very large bulky groups placed 4 amino acids apart, so 2 tryptophans separated by 4 amino acids, again, this is not something that can happen in the alpha helix. It's just too crowded, and you need to spread things out further to be able to accomplish these. So there are things that stabilize alpha helical structure. There are things that tend to disrupt it. Yes?
If an R group has hydrophobic tendencies, how would that play into the shape of the helix?
Okay, so alpha, if we have side groups that are hydrophobic, stacking them one on top of the other actually could be beneficial. It's their size, though, that we have to worry about in that context. If they're moderately sized, then it makes it such that they can form this very compact structure. So part of the beauty of the alpha helix is compactness. And as we talk about proteins folding up and adopting their final shape, compactness plays a huge part in this process. And so the alpha helix is good at getting very compact structures, provided that you have R groups that are not so big as to crowd one another out of the alpha helical structure altogether. Let's talk a little bit about beta sheeting. In beta sheeting now, we actually are going to orient adjoining R groups 180 degrees away from one another. So this is one arrangement. This is called anti-parallel. If you look at these arrows, what this is saying is that the amine terminus is over here. So this is it. So we have a free amine here, and this whole strand goes this way and then it comes back this way, and it goes off in this direction. This is called anti-parallel structure. This is the most common type of beta sheeting that is found. And if you look at this, if you look down at the bottom, you can see that our R groups are positioned down and then positioned up. And so this is a way of accommodating, let's say, two very large groups that are placed right next to one another. So if you had two tryptophanes in a row, this would be about the only way you could accommodate them. The problems arise when we look at the actual positioning of these groups within the beta sheet. So as we have 2 or 3 or 4 strands of beta sheeting, the R groups now are projected up. And if those are very hydrophobic, I mean, not very hydrophobic, very large, it may be problematic. You may not be able to maintain the beta sheet structure. If you have 2 negatively charged species that are positioned on different regions of your beta sheet, but now they're positioned right next to one another, there'll be repulsion. And so again, there'll be a distortion in the beta sheet structure. Okay, questions about this? So again, the phi-psi angles favor beta sheeting. Large hydrophobic side, I mean not hydrophobic, but just large side groups also favor this kind of beta sheeting, provided that as you bring parallel strands together, you're not pushing very large groups together or negatively or positively charged groups that repel one another, one from another. Questions? There is, yes?
So you say tryptophan is large. What terms, where's the difference of large and small? How different is large and small?
I would say anything that has more than a couple carbons sticking out on the other, at the side is starting to get large. So certainly tyrosine, phenylalanine, tryptophan, methionine, isoleucine, leucine, all of these are large side groups. Things that are more modest, well, and also if you have aspartate or glutamate, those have, again, long arrays of hydrocarbons sticking out from the peptide backbone. So those would all be large groups. Others, you know, an alanine is fairly compact. The serine would be fairly compact. Threonine, so starting to get a little bit on, you know, sort of medium in that respect. So, okay. Let me show one more slide here, and then we will. This is the other arrangement. This is called parallel beta sheeting. So again, we have the N terminus over here. The strand of amino acids then run this way, but they then have to go around, and then they come back and they go this way again. And then they have to find their way all the way back around over here to come back in a parallel fashion. That is, the direction of the amino acid sequence is going the same way. These are much less common, as you might imagine, because you have to have this thing, the peptide chain, go all the way around and then come back and lay down parallel to the initial strand. Okay, but this is called parallel, anti-parallel. They differ slightly in their dimensions. So this one, the distance between these, oops, if I can find my cursor here, there it is. The distance between these two R groups that are both up is 6.5 angstroms for the anti-parallel, the distance between these two R groups is 7 angstroms. So they're slightly different. You'll notice one other thing, that is that again, we have hydrogen bonding between every peptide bond and its neighbor. So here you can see we have the carbonyl of 1 facing the nitrogen with its hydrogen of this other strand, and there is hydrogen bonding. Here the carbonyl is going to be attracted to the hydrogen on this one. If you look at the parallel, you can see that the hydrogen bonding is not going to be as strong because you don't have these projected, the carbonyl and the hydrogen, directly at one another. They're offset at a bit of an angle. Okay, let's leave it here. Are there questions before we? Okay, let me see if I can move the story forward. As mentioned, we were a group of us from our local ward. We're going to hike this mountain in New Hampshire called Mount Monadnock over Thanksgiving weekend. We arrived, we camped for the night on Friday night. We got up Saturday morning and it had snowed, not a lot, but it had snowed, and we were just completely shrouded in fog in our camp. But the trail wasn't bad, and so it was determined that we would still do the hike. And so that was the determination. There was a young man, as I mentioned, a fairly new member of the church, who lived kind of in the inner city. And he hadn't spent time in the outdoors. Really hadn't had the opportunity. And when he arrived, we could tell immediately that he wasn't very well prepared. His shoes, sleeping bag, all of these things pointed to his not being very well prepared for this. Maybe I should drop this here. So, but we started off, and we started up the mountain. I was staying with this young man, Rory, because I think at that point I was the scoutmaster, and he was one of my scouts. And so the fathers and sons, the others in our ward, scampered off through the fog, and within a matter of a few seconds, minutes at the most, they were completely out of sight, and Rory and I started up the mountain. And we hadn't gone more than a few hundred yards before he stopped. And he was completely out of breath and was panting and said, "I want to go back. I don't want to do this." Okay. I said, "Well, let's just stay here for a minute and kind of catch our breath and see how you feel at that point." So we waited, and his heart rate slowed down, his breathing slowed, and we went on another couple hundred yards. And at that point, he was completely out of breath. And so we stopped again. Just, we're completely surrounded in fog. Everybody else is gone. We're there by ourselves. And he's feeling, he's not in good shape. And he's out of breath, and he wants to go back. And I said, "Well, let's just stay here for a minute, catch our breath, see how we're feeling in a couple minutes." So we just stop and wait, and his breathing slows down, and we're able to go on maybe another couple hundred yards. And so we repeat this, and it just seems like forever. He doesn't know where he's going. We don't know if we're close or how far away we are, and it's just very discouraging for him. But he continues to stick with it. We just move a couple hundred yards, and then we wait, and we move on another couple hundred yards. Well, we hadn't even I don't know how far we'd gone, but at some point, the others come back down. I mean, we hadn't gotten anywhere near the top of the mountain when everybody else had been to the top and were running down the mountain to see who could get back to camp first. But he continued, and we continued until we finally came above the fog. And now you could see very clearly the crest of the mountain. It's a granite top. It's very distinctive, and he could see that was the summit of the mountain. And suddenly his attitude and his perspective changed. Once we were out of the fog, he could see how far it was, and he believed now, based on how far down he could look, that he could make it. And so now, without any coaxing, he would move off until he just was out of breath, and then he'd stop and catch his breath, and then we'd move on. And indeed, he summited the mountain, and we made our way back down, which was much easier. My point in telling you this is that very often in life, we are just sort of in a fog. We are in a tunnel. We can't see the light at the end of that tunnel. We feel overwhelmed. We feel inadequate. We are really not confident that we can do what's being asked of us. This can be chemistry. This can be COVID. You name it. But if we continue, if we stay on the trail, if we keep moving up that trail as best we can, and then there will come a time where we'll be able to see what the goal is, and that we can make it, and that we will achieve it. And so my hope is that you will all stay with things and trust in our Heavenly Father to guide you, to lift you, to coach you, and encourage you, and that you will succeed in your lives, even when things seem dark and the way seems very long and hard. Thank you very much.